I welcome you all students for the online learning platform. So, we are in the process of learning the course warehousing automation through blended learning process. So, today this particular presentation will take us to unit 2 queuing theory for the next chapter queuing models. So, now we are learning about the queue philosophies and the queue mechanism. So, the customer behavior in the queue, all such things we are discussing. And now we learn about the numerical methodologies of how to solve a queue. All such things we learn here. So before we get into it, we'll go for the important concepts of Kendall's notation, how to represent the queue. So first thing, it is assumed that customers arrive in random order at queuing systems. See, before we get into a mathematical model of a queue, we are supposed to know the assumptions on what basis the queue is designed, on what basis the queue is modeled. So we are supposed to know all these things. So in the due process, what we learn here is the first thing, the customers arrive in random order at queuing system and their arrival can be described by the Poisson's distribution and inter-arrival times are described by exponential distribution. So now how to understand this? So let me take you to a very simple example. So the example is like this. For example, we are having one particular, say, some counter. Okay, this counter might be a food or whatever may be the thing. So now you have opened the stall by say 10 a.m. We have opened and we are waiting for the people to come. Okay, just we are waiting for the people to come to the stall by 10 a.m. We have opened and we are waiting. So as of now, none has come. Now the first customer has made their arrival at some time. Okay, somewhere. Let us not worry about the time. At some time we have got their arrival. Now this arrival, no, so their first arrival, it is considered to be Poisson's distribution. So it is default assumed. That's the assumptions what we make. Now first customer has arrived and he has not been served. Now he is in the queue, say maybe ordering or he's paying or he's waiting for his order to be delivered, whatever may be the scenario, but he has come and now he is in the system. Okay. Now next customer, second customer has come and meanwhile third customer is also about to arrive. So likewise they are there. Now this is called as inter-arrival time. Okay. So the first guy he came, so his distribution will be Poisson and then after whomever comes into the system will be considered as exponential system. That's the assumptions what we make. Okay. When we design a queue, so these all are the assumptions what we make. So now to clarify again, first arrival, that is first arrival alone is considered as Poisson distribution. Next is considered as exponential distribution. Why this exponential? Why not the same Poisson? See, Poisson is going to be a sudden occurrence, but exponential, when we plot it the same in the graph, okay, so what will happen is, say this is see, sorry for the graph, I'll just go ahead with a proper graph. So now this is the graph what we have. When exponentially you plot, it is how it is going to, that is it increases with respect to time. Okay, it increases with respect to time. So always we love the business to grow, no, we don't always something like dipping undulation nobody loves. Okay, so that is the philosophy why we go for exponential. So first arrival alone will be Poisson and the next after will be treated as exponential. So that is the understanding what we need to have here. Okay, we'll go for the next. Distribution of arrival process. Okay, now the entire system is considered to be into two halves. Now this is the counter. Now let me divide this counter into two halves. Somebody arrives into the counter and they get their service done and they go out. Say for example, if this is a banking, they came for some sort of money or something with respect to it. Okay, if it is a food stall, they came for a takeaway. Now the arrival, the distribution of arrival is considered to be pure birth process. This is another assumption. So pure birth process, it means that the customers arrive at the queue system and they never leave it. They came and they are waiting. Still they will be waiting till their service is done. So that is called as pure birth process. Why? Because we have learnt about the customer's behavior in the queue, balking, reneging as well as jockeying. No, here no such behaviors. So there is only one queue, until they get their service done they are going to be into the process, and that's where it is called as pure birth process. It is called as pure birth process. So that is nothing but distribution of arrival. So arrival is considered to be pure birth process. Okay. Then once their service is done, then they leave the counter obviously. So that is called as pure death process. So this is pure birth and this is called as pure death. That's what the next slide will take us to. So distribution of departures. So now the counter is there. So as we discussed, this is pure birth process, and post this is going to be considered as pure death process. So this is distribution of departures. So this is distribution of arrival and this is distribution of departures. Now the thing is, assumes that no customer arrives in the system while the service is continued for the customers already in the system. That is, they wait till their process is done until they leave the counter. Now distribution of departures, the same continuation. Now if there are more than one customers in the queue, if there is only one, obviously it has some sort of sense. Only one is there, his work is being carried out in the counter and it waits. Now if there are more than one, that's what, if the population, see as we discussed in the earlier slide, that is earlier discussion, capital N means it represents the population. So N means number of people available in the system. So these all are the notations what we discussed in the earlier. So if there is a population more than one in the system, okay, at a time t, at time t0, so their arrival rate is considered to be mu. Okay, their rate of arrival is considered to be mu. So this is what we call it as pure birth process is assumed to be mu. Okay, mu is the representation. So therefore customers will wait till their service rate is going to occur. Okay, so lambda is the arrival rate and mu is the service rate. So mu time, till the mu time gets over, they will be inside the process, and that is where we call it as pure death. Clear? So arrival and service rate both should go hand in hand. That is what the understanding is. Now, before we get into the further modeling, we should know who developed the system. Okay, queuing models are classified based on two things, that is special or some cases standard, and this is noted by D.G. Kendall. So D.G. Kendall was the person who found this concept, okay, in the form of ABC, and of course later on A.M. Lee also he added some symbols by name DC, and finally these things put together is called as Kendall's notation. So we'll see what is this Kendall's notation. So now we have got a column dividing the birth process and death process. So this is going to be pure birth process and this is called as pure death process, and it is distinguished by means of a column. So all these things put together called as notation. In short, it is called as notation, but actual term is called as Kendall's notation. So this is how it goes on. So now what all are the three elements present here means A slash B slash C in the birth, and in the death it is D slash C. Some cases even E might come, of course based on the speciality it might be there or it may not be there. Some cases C will be replaced by E based on the need, based on the necessity. Now A is arrival distribution, so default we believe this as, or we assume that as Poisson's distribution. So B is service time distribution, so service time distribution, and C is number of servers, how many servers are there. So if minimum one server should be there, then only that is considered as a queue. So more than one means based on the scenario it is going to be there, and here the significance of C is it is associated with the cost. Okay, more than one server we need to pay more. Then D is capacity of the system and E is queue discipline. Okay, some cases here also number of channels C might come into picture. So based on the scenario it will change. Okay, so to understand, so we have got Kendall's notation like this: A slash B slash C colon D slash C or E. So on left to the column, it is going to be pure birth process, that is arrival into the system, and here it is called as pure death process, it is exiting the system. How do they arrive and how do they go? So here it is going to talk about service, and this is going to talk about waiting time. So what is the waiting in the system? It is going to talk about. So this is what Kendall's notation is. So now we'll see with an example. Yeah. So this is first model. So model here is M1. Okay. So I'll write it here M/M/1. So first we'll decode this, then we'll go for the RHS. So first M is purely Poisson's distribution. I'll just erase this and I'll write again. Okay. So M/M/1. Okay. So M is going to be Poisson's distribution. M is going to be called as Poisson's distribution, and here the second category is again Poisson distribution, and one is only one server is available, only one counter is available. Okay. So under this notation we understand that only one is there. So waiting time will obviously it will be minimum. So now the second here infinity, the population is infinity. Okay, the population is infinity, and here FCFS is first come first serve, the queue model. First come, you arrive into the system first, you get the work done and you go out first. So this is what I wanted you students to recall the things what we learned on the earlier SIRO, service in random order, or LCFS, last come first serve. So likewise these all are the queue models. So here this is what we understand from M1 model 1. So this is going to be pure birth and this is going to be pure death, and here the population is from infinity and the queue behavior is FCFS. And the next case, unlimited queue, the same understanding. So here we have got an average rate. So here this is the one which is quite interesting. When you have got an infinite, it is understood that you can't control the arrival of the process. So that is where we have got average service rate. Okay. So don't get confused with all these things. So just have a simple understanding like this. So M1 colon infinity colon FCFS. That means, so here this is going to be a pure birth process and this is going to be pure death process. That is the first takeaway. This entire notation is called as Kendall's notation. That is second takeaway. And the third takeaway is, so Poisson's distribution is going to be represented by capital M, and here only one counter, that is one server is there, that is number 2. And here in infinite population, you can't have control, you can't control the population size, it is infinite, that is from the society, from the geographical location, likewise they come, and here the behavior is FCFS. You arrive first into the system and you go early from the system. That is the understand what you need to have. That much is sufficient for a warehousing purpose. Okay. If you are still interested to learn a lot, obviously we should get into operations research and management to learn a lot in this. Why? Because there are some 5 to 6 models are there. So here as far as our syllabus, we have got only single server model. Now this is what we need to know at any point of time, the notations. Okay, so notations, please be very cautious enough, note down all these things in a separate page, so that because in the problem, when we get into the numerical problem, what happens is we will have the problem being given. So we need to, that given data has to be noted in this particular formula, then only we will be able to substitute the same into the formula, and then we will go ahead to solve the problem. Okay, so in this online platform I just solved 2 problems, so don't worry about this numerical problems. During our offline class as well as during the doubt clarifying sessions, we will solve say some 5 or 6 more problems. Okay, so within the prescribed time we can solve n number of problems. So only thing is understand them, understand the notations first. If you are able to understand the notation, then solving of problem will be very easier. Okay, so we'll start the problem. Okay. So before we start, you need to know these formulas. So first formula, see here, note down the notations because the formulas will be in the notations. So lambda means arrival rate. Okay, so you should have an idea. You are never supposed to forget. Lambda means it is going to deal with the arrival rate. Okay, rate per hour. So mu will be service rate. So that is another important thing. ls means expected number of customers in the system, L suffix S. So it is going to be in the suffix case. The same next L suffix Q. Q means number of people or length of the queue. Here length of the system. So actually length is just for understanding. So actually it is expected number of customers in the system. So L suffix X is equal to lambda divided by mu minus lambda. Okay, expected number of customers in the queue, L suffix Q is equal to lambda squared divided by mu into mu minus lambda. So note down this two formulas. Actually we have got 5 formulas, so note down these two. The next, third, again I want you students to keenly observe the notation W suffix S. So W is waiting time in the system. Okay. Next, W suffix Q, waiting time in the queue. Okay. So here the formula is L S, the one what we calculated in the previous, divided by lambda, arrival rate. Okay. So similarly here L suffix Q divided by lambda, service rate. Now we'll get into the problem. Okay, we'll solve the numerical problem. So first we'll understand the question. A television repairman finds that the time spent on his jobs has an exponential distribution with a mean of 30 minutes. So this is the first. Let me change the color. Just a minute. And yeah. So this is the, no, yellow is not visible. I'll change some other color. Yes. So 30 minutes, this is the first data what we have got. So exponential distribution with a mean of 30 minutes. So it is the time what is spent. So that means service time what is spent on his jobs is 30 minutes. If he repairs the sets in the order in which they came in, and if the arrival of sets follows a Poisson distribution with an approximate average rate of 10 per 8 hour a day. Okay, arrival rate. So Poisson distribution. So here you can see arrival of sets follows a Poisson distribution with an approximate average time of 10 per 8 hour a day. What is the repairman's expected idle time each day? That is question number 1. And question number 2 is how many jobs are ahead of the average set just brought in. Okay, students, just first understand what is there. So there are 2 data given and 2 outcomes are there. So 2 questions are there. The first thing is there is a TV guy who repairs. So for each TV is going to spend 30 minutes. For each product is going to spend 30 minutes to repair. Now arrival is like this. He works in a day, that means 8 hours only he works a day, and he gets arrival rate is 10 per 8 hour. For each 8 hours he gets 10 products. So now 2 questions have been asked. One is idle time and what is the average set brought in, average arrival into the queue. Okay, now we'll solve the problem. I think space will be sufficient. I am not switching off the camera, so we'll start solving the thing. So first, mean. Where is, yeah, I think the color is visible properly. So mean is 30 minutes. The mean is 30 minutes. That is the arrival into the system. And the another important thing is lambda. We wanted to know the lambda arrival rate. 10 TVs comes for 8 hours. 8 hours is the total duration what he works. So therefore 10 per 8 hour. This is the given data. So now let us simplify. Dividing by 2, we get 5 by 4 sets per hour. Okay. 5 by 4 sets per hour. So now we wanted to know the next case, mu. So mu is taking 30 minutes, right? So 1 divided by 30 per hour we wanted to know, so we'll multiply by 60. So therefore when we do approximately 2 sets per hour. Okay, so 2 sets per hour, so that is the thing. Now we'll solve the problem. So with this two datas we'll solve the problem. So here expected idle time. So that is the first question what has been asked. So I expected idle time. So first we'll understand what is the busyness. So idle time, out of 8 hours, so lambda by mu, that is the thing. So lambda 8 into 5 by 8. So when we solve, 8 gets cancelled. So therefore 5 hours. So this is the idle time. So 5 hours is going to idle. Okay. So actually this is utilization. So we wanted to identify the idle time. So utilization is out of 8 hours. So this is the work what he does. So 5 by 8. So total idle time. So total idle time. So out of 8 hours, 5 hours is engaged. So that means 8 minus 5. So 3 hours are going to be the idle time. Okay. So this is how we calculate the idle time. Then the next question. I'll change color for that. Yeah. Next. The thing is expected average number of TV sets, that is arrival of TV sets. So in the bracket let me put as arrival. Okay, that is the next question which has been asked. So now we know into the system, not to the queue. So L suffix S is equal to lambda divided by mu minus lambda. That's the formula. So therefore we will substitute lambda is 5 by 4. Already we calculated. So divided by, so mu is not 2 minus 5 by 4. So upon simplification, let us simplify this. So upon simplification we get 5 by 3. So that is 2 sets per hour. Okay, 2 sets per hour will be the average thing. So approximate, because we can't have decimals now. So that is where we will have 2 approximated. So even in the bracket we can put it as approximate. Okay, so this is how we solve the problem. So have a keen understanding. First put it them in with respect to the notations, and from the notations we can solve. Second problem and the last. So as I told you, we'll have two problems, and now we'll solve the next case. A warehouse has only one loading dock manned by a 3-person crew. Trucks arrive at the loading dock at an average rate of 4 trucks per hour, and the arrival rate is Poisson distributed. The loading of a truck takes 10 minutes on an average and can be assumed to be exponentially distributed. The operating cost of a truck is 20 per hour, and the members of the loading crew are paid at 6 each per hour. What would you advise the truck owner to add another crew of 3 persons? Okay, so I'll just go to a fresh slide. Okay, so we'll solve. Lambda is given as 4. The next loading time is given as 10 minutes. Then the payment amount is 20 rupees for truck. Okay, then 6 per hour is for the case of crew, that is for the men. So now this particular problem is having two halves. The first thing is we are going to come out with the decision whether the existing mechanism itself can go ahead with, or we are supposed to come out with the second, that is crew adding 6 more members. Which one is going to be beneficial? So that is what we are supposed to do. So apart from queuing theory, we are supposed to understand the basic problem, and queuing theory will assist to solve. So we'll see how to solve this. So now we'll take the case 1 as existing. Okay, let me put it as 1 existing. So existing, the total cost is going to be like this: crew cost, whatever the thing we are spending on the crew cost, plus their rate, what we offer to them. Okay, number of, that is numbers, let me put like this, into numbers. So now we'll solve. How means, how we'll get the crew cost? Number of loading peoples, let me put as loaders. Okay, number of loaders, into our rate. What is the per hour rate they are going to? So let me put this in the bracket, then plus waiting time, that is in the system WS per truck, WS of a truck, into their arrival rate. How many trucks they come? That is lambda, into what is the rate we pay for them per hour. So this is the formula. This is the decoding what we do. So let me put 6 loaders are there and they are paid, 3 loaders are there, they are paid 6 per hour. That is the thing what we have got. So this value plus 1 divided by 6 minus 4, okay, lambda, okay, that's the WS formula, into 4 is going to be there, lambda value, into the rate paid for the truck is 20. So when we solve this, we get rupees 58 per hour. So this is the existing. Now we'll go for the proposed. Proposed is we are going to add 3 crew, that is a crew of 3 people extra. That is what is given in the problem. So 3 crew. So now the same total hour cost is equal to 6 rupees into 6 people. Now 3 we are adding, 6 into 6 plus 1 divided by, now it is not 6, now 12. 12 minus 4 into, rest is going to be the 4 into 20. So when we solve this, we get rupees 46 per hour. Okay, so obviously the proposed method is quite good, so we suggest to go with the proposed method. Okay, so this is how we are supposed to solve problem, though we do it on the online platform. Only 2 problems we could do, and rest we'll solve in the offline class. Okay, so with this we'll go for the summary. So to summarize, this particular presentation took us to the queue models. We saw how, what all are the assumptions are there in a queue, then the notations used in the queue, how the notations are represented by means of using colon. So before it is going to represent the pure birth, that is on the left side to the colon, on the right side on the colon it is going to represent the pure death process. So we saw that particular work, and followed by we solved numerical problems. Actually we had 5 formulas, only 2 problems we are able to solve on the online platform. So as usual, students, please note down the doubts, what are the things you have got. So therefore those doubts we shall solve, that is we can get the same thing solved in the online platform as well. We'll solve few more problems in the offline classes, okay, as well in the doubt clarifying sessions. Whenever we just meet on the weekends or the off timings, we'll discuss those things. Okay, so thank you for your presence, and with this we finish the second chapter in unit 3. Okay, thank you.